Okay, so I don't come to North America frequently, so I decided to talk about two things that I've been working on. One is Magnetar oscillations, and the other one, if time permits, I want to talk about how to use pulsars to measure gravitational waves. So let me just start with some physics preliminaries. This is the physics I want to talk about as the physics of magnetic fields in conducting fluids. This experience is different from this situation is different from our everyday experience. But in astrophysics, the fluids are highly conducting. And so what happens to magnetic fields in these fluids is that they get frozen into the medium. And the reason is that because if you try to move a fluid relative to magnetic field, there is a Lorentz force that would cause a current, and that's not allowed. So, so the way the system resolves this is that the fields are essentially frozen into the fluid. And then if you write down the Maxwell stress tensor for magnetic fields, you'll see that magnetic field possesses tension and pressure. The tension is along the field lines, and the pressure is perpendicular to the field lines. So the field lines like to push away from each other, and they also like to be straight. So now if you take this picture, imagine these were straight lines, and then you displace the lower part of the picture to the left. Okay, the tension of the field lines will try to make it straight, so you'll send a kind of a wave, like a string wave, a tension wave, along these field lines, and these are called Alfven waves. And they go with the velocity which is proportional to the strength of the magnetic field and inverse proportional to the square root of the density. Now, this is all physics I need for this talk. Now, magnetars. Magnetars amazingly were predicted theoretically. These are ultramagnetized neutron stars. They were predicted theoretically by the current citizen Chris Thompson and Rob Duncan in '92. And I must say nobody believed them for many years, but now it's a generally accepted notion. There is this class of neutron stars which are extremely magnetized, which have magnetic fields of about 10 to the 15 Gauss. These fields are not relaxed inside the magnetar. So this is a cartoon of a magnetar. It has a crust, it has a fluid core, and the field lines inside the magnetar, they're not straight, they're curved. So there is a lot of free energy stored in this type of fields. And this free energy is gradually released from this neutron star. And it can be released in two ways. Either this energy comes out as X-rays from the surface, so this free energy of the field goes into heat, and then this heat is radiated from the surface as X-rays. Or sometimes this energy can be released violently, okay, and then you have flares. So the objects which are releasing this magnetic energy, the magnetars which are releasing magnetic energy gradually are called anomalous X-ray pulsars, and those ones which are releasing this energy violently are called soft gamma ray repeaters. And in particular, there has been 3 amazing releases of energy from 3 soft gamma ray repeaters. These are the so-called giant flares, 3 giant flares. The first one was in 1979. Then there were 2 more recent ones, 1998 and 2004. And these are truly spectacular astrophysical events. They actually have influence on our everyday life on Earth in the sense that the radiation from this, which is coming from these flares, is affecting the ionosphere in a very serious way. So the radio communications are affected. The way these flares are structured is that you see a burst of gamma rays and X-rays, which is very bright, and then there is a tail. There is a sort of a slow decay in X-rays of these tails. Now, one of the interesting things over the last few years is that in all of these 3 flares, well, actually, in the last 2 flares, I should say, 98 and 2004, people have discovered in the tails that the X-ray luminosity has some characteristic oscillation frequencies. So in this figure, what's plotted is a dynamical power spectrum. So let me explain to you how this is done. What the observers do is that they take a light curve. X-ray luminosity is a function of time. And they measure this light curve for hundreds of seconds. And what they do is they take a little time window, let's say 4 seconds, sometimes a little bit smaller, and they move this window along the time axis. And in each location of the window, they take a Fourier transform, all right? And they plot a Fourier transform on the y-axis. So that's why I have frequency in hertz on the y-axis, and I have time in seconds on the x-axis. And then black means that Fourier transform is high in that location, and white means it's low. So this is the so-called dynamical spectrum. So this is the discovery plot of these quasi-periodic oscillations, and you see this very characteristic signal here at about 90-something hertz, 95 hertz, this peak. So this is a so-called QPO peak. And then you see in the same plot, you see this lots of structure at around 20 hertz. Actually, a little bit. Some of it is a little bit below. Here is sort of 18 hertz, but there are other structures. So there's a lot of stuff going on here, and this is sort of a longer term than this feature, which appears up here at 90 hertz. So this is a discovery plot. All right, of this. And so this is a discovery plot for the flare, which was the last one in 2004. And then Anna Watts and Todd Strohmeyer, they have reanalyzed the previous flare in 98, and they found a whole variety of these frequencies. So this is the summary of all the frequencies that they found. These are sort of numerical values at which they have identified these QPO features. And this is the duration with time where these features were observed in time. So you see that some of these features, especially the lowest frequency features, last for hundreds of seconds. Okay, so this is a long-lived phenomena in the tail of the burst, and some of them have much shorter lifetime, more intermittent. All right, and what you see, the oscillating curve here, this has nothing to do with these oscillations, right? The oscillating curve here is just the rotation of a magnetar. Magnetars are typically rotating very slowly with periods of about 5 to 10 seconds. So these are very slowly rotating neutron stars. Now, people got excited about these QPOs because one of the most natural explanations that were immediately proposed is that these are oscillation frequencies of proper modes of neutron stars. Okay, so what frequencies are we talking about? We're talking about several tens of hertz. Okay, this is the characteristic frequency of these guys. And you can immediately see that this cannot be the fundamental modes of neutron stars, because the fundamental dynamical frequency of a neutron star mode is in kilohertz. Okay, so this must be modes restoring force of which is not gravity. All right, and the most natural restoring force, which is not gravity in neutron star, is the elasticity of the crust. So this must be shear modes of the crust. It's called torsional modes, right? This is a type of modes which don't cause density perturbations of the neutron star material in the crust, but instead they cause the shear, then the elasticity tries to restore the shear. Okay, so this was interpretation number 0 that was put forward. And it doesn't work, this interpretation. There are 3 reasons why it doesn't work. The first reason is that 18 hertz, this low, very long-lived feature that you saw before on the previous diagram, that's too low. Torsional modes don't have frequencies which are too low. And that may seem that it's only too low by a factor of 2, lower than the fundamental torsional mode of the crust. But a factor of 2 difference in frequency means it's a factor of 4 difference in shear modulus. And we know shear modulus of neutron star crusts with higher precision than a factor of 4. Okay, and the second caveat in this picture is that these quasi-periodic oscillations, phenomenologically, they're highly intermittent, some of them, right? So the picture where you take a neutron star and hit it with a hammer, and then you listen to it, like you listen to the tuning fork, slowly decay in tone. That picture doesn't work. There is clearly, just by looking at these frequencies, there is clearly a very rich dynamics which is going on. So it's clear that if it's some vibrating oscillator, it must be intermittently driven. It's not just the aftershock of the flare. And the third objection, which is the most serious one, is that you just cannot have isolated crustal torsional modes in such strongly magnetized neutron star. And the key issue here is a high magnetic field. Let me explain to you why this is the key issue. So let's imagine a cartoon of a neutron star. This is a neutron star. This is its crust. Let's take the simplest possible magnetic field configuration. So the field lines are straight in this picture, okay? These are the field lines. And let's consider, just for the argument's sake, let's consider a deformation of the crust, which is just a pure twist. You've taken, fixed the crust bottom, fixed the crust top, and you twisted it, okay? And then you let it go. If you didn't have magnetic fields, indeed you would have a torsional mode or a collection of torsional modes which are living purely in the crust. But these magnetic fields, remember, they're just like elastic strings, okay? And they're also frozen into the fluid, both into the core fluid here and also into the elastic solid of the crust. So these are like things which are connecting immediately the crust and the core. And so as soon as the crust begins to move, it will send outplane waves into the core. And these outplane waves, they couple the core to the crust. And it turns out that this coupling has extremely short time scale. The magnetic coupling between the crust and the core happens on a time scale of a fraction of a second, from 1% to 10% of a second. And that's because the field is so strong. The restoring force of the field is almost as strong as the restoring force from the elasticity in the crust. So you can't have isolated torsional modes in the crust without considering dynamics of the whole system as a whole. So you've got to consider the global, the dynamics of the global system. Now, I will show you in a second that when you do the normal mode analysis of such a system, that for a reasonable range of parameters, the global torsional modes of the whole system don't actually exist. All right, let me explain to you qualitatively why this is so. Let's suppose the opposite. Let's suppose that there was a stable global torsional mode which existed in the crust. Okay, and this normal mode had some frequency. Now let's think about dynamics of the core. The way I've chosen magnetic field in the core in this very simple example is just sort of these straight lines. And now I'm, for simplicity, considering only twisting modes. Okay, so these are m equals to 0 modes of the star. For these modes, the motion of the fluid is purely in the azimuthal direction, both of the crust and the fluid in the core. And it's very easy to show that if you take a cylinder, some cylinder with a center around this axis of symmetry, then the fluid motion on the cylinder will not be coupled to those on all other cylinders. So the cylinders, they're magnetically decoupled from each other in the core. The only coupling they have with each other is through the crust. Okay? So, and each of the cylinders, it has its own set of overtones which are living on these cylinders. So you have the whole continuum of modes. You have the whole continuum of modes which are living in the core of this neutron star. And it turns out to be the general property of MHD systems, that they can support continuum of MHD modes. Finite MHD systems can support continuum of MHD modes. So in particular, in this example that I've chosen, if I have a twisting vibration of the crust, there will be a cylinder which will be in resonance with this vibration. Okay, the way I've drawn the picture, there will be a cylinder which will be in resonance. And so the vibration of the crust will pump will pump in resonance some standing wave on the cylinder. So now let me show you what happens if you do this problem and compute the normal modes of the system. So how do you compute the normal modes of the system? Remember, I'm considering only twisting modes which have m equals to 0. So they completely symmetric with respect to some axis of symmetry. So the way computational procedure goes is that you set up some periodic motion of the crust. You assume that the crust is displaced periodically. And then you compute the response of the core. You compute magnetic response of the core. And that you can do because the core is just a bunch of strings. Okay? So you can solve this problem. If you take the end of the string and you move it periodically, you can calculate how the whole string will move. That you can do quite easily. Then, once you compute how these magnetic strings move, you compute magnetic back reaction, and you put it back into the equation of motion of the crust. And when you do this, amazingly, you get a 1D Sturm-Liouville problem for the displacement of the crust. All right? And as you know, 1D Sturm-Liouville problem, there is an eigenvalue, which in our case is a complex frequency. So you search for a complex frequency of this mode. Okay, maybe I'm misusing the terminology. You get a second-order differential equation which depends on some set of parameters, and in general that can be complex. Now it turns out when I compute the response of the core, I put a little bit of damping in the response of the core just to control my resonances. Okay, so that's what I'm doing, and I plot this damping on the x-axis. All right, this is the numerical values of the damping that I'm choosing. And on the y-axis, I plot the imaginary part of this complex frequency that I'm finding. All right, and so these curves here, these are these computations for several values of magnetic fields. The upper value has magnetic field of 10 to the 15 Gauss. The lower curve has magnetic field of 10 to the 14 Gauss. And so I go through a sequence 10 to the 14, 2 times 10 to the 14, 3 times 10 to the 14, 9 times 10 to the 14, 10 times 10 to the 14 Gauss. And for each of this curve, I obtain the imaginary part of this complex frequency of the mode as a function of the damping that I put in to regularize the response of the core. Okay, now you see several amazing features of this. The first amazing feature is that in this region, essentially all of these curves are horizontal. So the imaginary part of this complex frequency does not depend on the details of this damping that I put in to regularize the response of the core. Right, so actually it turns out that that's what to be expected, because the imaginary part of this complex frequency is determined essentially by Fermi's golden rule. Okay, you have some system has some macroscopic degree of freedom. In this case, the motion of the crust, and then this system is coupled to a continuum, and the rate with which the system is pumping energy into a continuum just depends on the density of states at the continuum on resonance. Doesn't really depend on how the continuum modes are damped. So this is this you know this from quantum mechanics, but exactly the same argument works in classical mechanics. So that's why these curves are flat. Okay, but another remarkable thing is that when the damping becomes smaller than some critical value, for each of these values of magnetic field, the mode fails to exist. All right? The normal mode just doesn't exist at those values. This solution has this equation that you write down. It has no eigenvalue. And this is, even though this is somewhat surprising, but this result is actually turns out to be quite well known in a different context in the physics of oscillations of coronal loops, where you have in the sum, where you have very similar conditions. So the conclusion of this is that, and actually, so this damping rate at which the mode fails to exist, you see where it happens. It happens here for each of this curve. And this damping rate is actually quite large. So the realistic dampings that exist inside magnetars, they're a fair bit smaller than this this endings of this curve. So you really need to consider time domain simulations to understand how these systems behave. Doing the normal mode analysis is no good. You need time. Yep.
What does the real part look like of these lines?
The real part, okay, the real part is close to the modal frequency of the crust. The torsional modal frequency of the crust, close to it.
And you're saying if you plot both of them, they both stay unchanged as you change this gamma, and they both suddenly disappear. Like
Yes.
If you had two plots.
Yes. Yes.
And just to numerically, so you set up what a lattice of grid points, and you
Yes.
find the eigenvalues of a let's say 100 by 100 matrix.
No. Well, you get a differential equation, right, with some boundary conditions. The boundary conditions are the equator and the pole, right? And then you use one of your favorite methods of solving differential equations. You use like a shooting method to satisfy both boundary conditions. And you find that for these gammas, you can find the complex eigenvalue which shoots to the right boundary. And for gammas smaller than that, you cannot, no matter how...
But it's a linear problem, so in principle, you can put it on the lattice, and I can write a different equation over your angles.
Yes.
And I can feed, and then I have a matrix that relates my points to each other.
Right.
And I call my favorite Leiden routine, and if I have 100 points, it'll give me 100 eigenvalues, regardless of what I feed it, right?
Yes, but I would say that, I mean, I haven't thought about this from this point of view, but I would say that then you probably wouldn't converge if you take larger number of points. So for each finite number of points, you would converge to some value, but probably wouldn't converge to a value if you take larger number of points. But there is a qualitative reason why this eigenvalue. So this is not, even though this is a new result in the context of magnetars, this is well known in the case of oscillations of coronal loops, where you have the same thing. You have a continuum of Alfven modes, and then your global oscillation is coupled to this continuum. So people have thought about this problem before. I'm not the first one to think about this problem. And
So the damping that does occur is the feeding of these normal mode oscillations, when you do have modes.
yeah,
Feeding of the normal mode oscillations into Alfven waves.
into Alfven waves which are damped.
In the interior of the star.
Right.
So the interior of the star ultimately just heats up.
Heats up.
Due to the thermal damping.
Right.
of the Alfven.
Exactly. So, but all of this is confirmed by time domain simulations. So I'll show you time domain simulations shortly. Now, before I do time domain simulations of the whole magnetar, let me show you time domain simulations of several toy magnetars. Okay. So the toy magnetar I choose is very simple. It's a pendulum, and this pendulum is meant to fake one of the crustal modes. So I choose the weight of this pendulum to be 1 kilogram, and I choose the proper frequency of this pendulum to be 1. Okay? And then on top of this pendulum, I hang many tiny oscillators. Each of these oscillators weighs 1% of a gram, and I have 10,000 of these small oscillators. So in total, they add up to 100 grams, all of these oscillators. And they have length which varies through some range. And this range is chosen such that one of the strings in the middle has the same proper frequency as a big pendulum. So there is a resonance, okay, somewhere between this big pendulum and one of the strings. Not exact resonance, but approximate resonance. And then what I do is that I deflect this pendulum, and this mimics the strained crust of the magnetar. And I wait until these strings sort of all hang down at rest, and I let it go, let the system go, and see what happens. and I watch the displacement of this pendulum as a function of time. Okay, now the first thing that happens is that the amplitude of this pendulum, so this is displacement as a function of time, the amplitude of this pendulum is decaying exponentially as a function of time, all right? Because this pendulum is essentially feeding its oscillational energy into oscillation energy of all these little magnetars. And when I first saw it, I thought, well, okay, nothing interesting. But then I noticed that there is some residual here, okay? There is some residual small oscillation here. So I zoomed in on this oscillation, and that's what you see, all right? You see this exponential decay of the amplitude of the pendulum. And if it was a real normal mode, okay, if this system was a real normal mode, then this exponential decay would continue if I damped sufficiently strongly my little penduli. But because my little penduli are not damped, there is a transition from an exponential decay, right, of the big pendulum to some residual motion, which is more like a hyperbolic decay. All right, so this instead of exponentially decaying curve, it has 1/t decaying curve. Moreover, if you look at this, you see clear quasi-periodic structure here. Okay, you see clear peaks. See this little peak? So let's take a Fourier transform of this residual part, which is shown here. This is a Fourier transform. And you see a little peak here and quite a big peak there. And the frequency of the original pendulum was here. So it wasn't where the Fourier transform of these two peaks are. Okay, so the original pendulum frequency doesn't coincide with these peaks. So, but what is the origin of these QPOs, so to speak, QPOs? Well, it turns out that this is just the largest pendulum and the smallest pendulum. Okay, so this is the end points of this continuum range. The lowest point of the continuum and the highest point of the continuum. This is what is showing in this residual. So it's clear that this residual motion is the response. Okay, you've pumped essentially all of your energy into the little oscillators, and now they're swinging back and forth, and they're pushing and pulling on your big pendulum. And this is how a system responds to it. And for some reason, it is showing the frequencies of the largest pendulum and the smallest pendulum. So the special point of this continuum range, they show up in the motion of this big pendulum. So why? The question is why is it so? And so here I've plotted the phases of the small oscillators. So remember the frequency of the small oscillators, it ranged from 0.5 to 1.5. So here I just show the last 10% of this from 1.4 to 1.5. And you see that these phases actually are quite linear, right? And they do these 2π jumps. All right, but if you think about how these oscillators are pulling on the big test mass, because these phases are all over the place, they average out, right? This oscillator and this oscillator, they have a phase difference of π, and they're pulling this big test mass in the opposite direction, so they average out. And the only oscillators which don't average out is at the end, okay? Because these guys up here, they don't have a counterpart down here which would average them out. So these guys up here, they act coherently. They push and pull on the test mass coherently. So that's why they show up as a quasi-periodic oscillation acting on this big test mass. And if you want to formulate it mathematically, take a Fourier transform of any function with some sharp drops. And you'll see that this Fourier transform will give you, after late times, this Fourier transform will give you the characteristic values which correspond to this sharp drops in the. Am I saying this right? Take some function of frequency which has some features, okay, like a sharp drop, and take a Fourier transform of this function, which should give you time domain function as the function of time. And at late times, you'll see the sharp features in the Fourier transform. They all show up at late times.
The late time states are alternating oscillators at a phase of each
yes, I mean the number of oscillators which are in phase with each other, it keeps reducing. So that's why it decays gradually, all right? But not exponentially, it decays as a power law. Yeah. And actually the decay law of this power law becomes more shallow if instead of considering some linear spectrum, if I consider a spectrum with inflection. So here I have these little oscillators which start with some length, they become longer and longer, but then they go back, they become shorter again. Right? So there is some inflection, and there is a high density of states of oscillators of this length. So now I make the same numerical experiment, and again, initially I see the exponential decay, but then now, even with the naked eye, you see this signal with large QPOs, okay? And it turns out that these QPOs are really slowly decaying. So they have decay rate as 1 over square root of time. So that's exciting because it may be that our Magnetar oscillations, they're showing some features of this Alfven continuum, okay, which is existing in the core.
But in this case, you could also have taken your 10,001 normal mode, and this machine has 10,001
right.
normal modes.
In this case, you could, yes.
And there you would conclude that nothing is decaying, that all the modes are periodic, and all you've done is taken an initial state, projected on the 10,001 modes,
right.
and watch their passive
right.
phase mixing.
Right. But of course, if you have continuum, then you can't find normal mode anymore. If you have finite number of oscillators, of course, you can always find normal mode.
The other thing I'm wondering about is, like, this is basically like a Fermi-Pascal problem.
No, it's not Fermi-Pascal.
You don't have any coupling directly between these.
No.
So
No, the only thing is, so this is something which I don't quite understand completely, is that these oscillators, they can couple to each other via through the big pendulum. And then, because, like, for example, this oscillator and this oscillator, they have similar frequencies, they can talk to each other through the big pendulum.
Right.
So there may be some kind of waves which are propagating through these oscillators because they keep talking to each other.
Right. But what I'm getting at is you see this very regular phase evolution.
Yeah.
Which is sort of measure zero in the phase space of most Hamiltonians.
Right.
So normally you'd expect that you get some chaotic motion, right, where you mix up the phases. So if you put any other sort of coupling between these things, for example, I expect you'd see you destroy all this KM.
Okay, maybe.
And then you get, might get very different dynamics then.
But I think, well, wait a second. But basic dynamics is that you have big modes of the crust coupled to lots of small modes in the core.
But no coupling directly between the small modes.
No coupling directly between the small modes.
Right.
So you assume that you can decompose, if you fix the boundaries of the crust, you assume that you can decompose the core into lots of...
This approximation, there's no coupling directly between the small modes actually makes sense physically.
Okay, that's an interesting point. I haven't considered it.
So this is somewhat similar to that heat from the sense that you are reaching energy competition.
No, you don't. You don't have you don't really have a real equipartition, not on those time scales.
You don't have it.
To reach equipartition, you have to have nonlinear couplings between modes.
But in a way, if you're sort of decomposing big motions for small motions, it's sort of reaching that linear. Anyway.
Okay.
You are pushing out energy to everything.
Right, I push it, but it's not equipartition. It doesn't equipartition.
Now, this system, if you actually calculated all 10,001 modes, and you had inflection points like that, does it correspond to, and you plot the spectrum of those 10,001 modes, then what does that mean? Does that mean that you have points where you have very close spacings of resonances?
Okay, that's probably true, but I haven't done this exercise. But it sounds plausible. Okay, now how do you simulate the real Magnetar? Okay, this is just toy models, right? How do you simulate the toy model of Magnetar? Well, there are several basic steps. The first basic step is that you decompose crustal motion into discrete modes of the crust proper, okay? And then you decompose Alfven motion on each cylinder into some standing waves, because these are really sort of violin modes on each of the cylinders. And then what you have to do, so this is a non-trivial step, is to calculate how these two interact with each other. I'd say it's non-trivial, but it's also not very hard. You just have to solve the following problem, actually. You take a string, you attach one end of the string to the wall, and then you move the end of the string with some time dependence, and you have to calculate how the string moves. And the easiest way to do it is to decompose the string into standing wave, and you see how each of the standing waves is driven. So that's how you do this problem. And so far, it is exact. All right? So far, this treatment is exact. But now, of course, these are torsional modes, but on each of the cylinders, you have this torsional standing waves. Now you regularize it, okay? And the way you regularize it is also quite well controlled. First, you take, instead of taking infinite number of cylinders, you take finite number of cylinders. And then secondly, you take a finite number of standing waves on each cylinder, okay? And of course, you consider a finite number of crustal modes. And then you run it. So it's a simple harmonic oscillators all coupled to each other. You can integrate them using some preferably energy-conserving integrator like Leapfrog. But it doesn't actually matter. You can do simple Runge-Kutta. This precision of this problem is not requiring very high sophistication with the integrators. So I have done this, and I have chosen, in this illustrative example, I have just considered two basic modes of the crust. All right, and I have considered 1,000 cylinders, and each cylinder has 10 overtones in this problem. And I have picked some particular point on the crust, and I monitor what happens to it. And so initially you see this decay, exponential decay, and then you see this structure, which is the crust responding to vigorous motion of the core, which was excited by this original motion. So this is a Fourier transform of this part, okay? And you see this multiple peaks. Well, the way to do it is to do what the observers do. So let me just do what the observers do. So this is dynamical spectrum of this system. So this is dynamical spectrum of displacement of some point on the crust. And you see some features here, okay? If you look at this picture, so again, I take a window. My window is 4 seconds. And I move this window along the time axis. And in each window, I take a Fourier transform. And I put this Fourier transform on the frequency axis. And I see QPOs. Okay, I do see QPOs. This is the lowest QPO, right? Which corresponds to the longest cylinder, actually. Sort of the crossing time, because this is this special inflection point, right? It's the longest possible cylinder in the problem. This location is its overtone, okay? But you also see some intermittent QPOs here, right? Probably you can see it better than me. You see these intermittent structures which continue like this. And you also see some excess power here. Now, where are my normal modes of the crust? That's where they are. So I took just two normal modes, one at 90 Hertz, one at 40 Hertz. And you see that somehow around 40 Hertz, this is where all of these intermittent QPOs appear. And also here, although it's sort of less clear, but you definitely see some excess power, intermittent excess power at this frequency as well.
Is that spectrum converged in terms of the number of cylinders you take?
Yeah, it's converged. It's converged. So I've tried different things. It's always gives different integrators as well. Always gives the same answer. Now you see these drifting QPOs, which I don't really understand. Okay, so in my toy models, I didn't see these drifting QPOs, but here I see these drifting QPOs, and it seems that when they cross the crustal frequencies, okay, so it seems that they probably exist in the continuum, but when they cross the crustal frequencies, then they get amplified and they produce this intermittent structures. And you see these low frequency QPOs, okay, right at the frequency where you need to see it, around 20 Hertz. All right, and these are long-lived. So let me remind you about observations. In the observations, these are the observations. You see these long-lived, low-frequency structures, and you see this more intermittent things at higher frequencies. And this corresponds quite well with this qualitative picture that you see this long-lived QPOs at frequency of about 20 Hertz. And you see more intermittent structure up here. So there is a qualitative agreement there.
So again, this is a linear system with 10,002 modes of harmonic oscillator.
Yes.
That's the model that goes
Right.
on. And that thing, if you put it into, if you diagonalize it, would have a lowest eigenvalue, which is saying exactly 18 hertz if you did the diagonal.
I don't know. I haven't diagonalized the system, but it sounds plausible. I mean, what you're suggesting sounds plausible. I just haven't done it. It would be useful exercise to do. Okay, so I think there is a good qualitative agreement. And the picture then is that the intermittent QPOs, which appear at several tenths of hertz, these guys correspond to crustal frequencies. And these long-term QPOs here, they correspond to special points of the Alfven continuum in the core. Okay.
In your simulations, you see the drifts down to lower frequencies at late times.
Well, mostly it's at early times. You see, there's really.
Early times, yes. But if it were, because it's still a high frequency, but the time scale below, if you really are only, kicking all 10,002 modes for some initial setup, then the fundamental mode is just periodic with whatever you excited it with initially. So if that were 18 hertz, let's say, in this particular system, then the 18 hertz is still very short compared to your time scale course. So I would have expected, it immediately gets excited and it stays periodic at 18 hertz and just decouples. So somehow you don't see that in this picture.
No, somehow you don't see that. You saw it in the simpler model, and I suspect that this is to do that this 18 hertz, it has relatively low leverage. So remember, this is the lowest, the longest cylinders. Okay, so they have the small radius, so they actually don't have that much leverage. I think it takes a while for them to show up asymptotically before all of the other modes of the continuum decohere with each other.
So that's a normalized plot. So in fact, it's still consistent that your 18 hertz
This is it. This is it.
Initially, it just happens to be lower, so it doesn't show up on the color scale. That's what you're saying.
Well, it doesn't seem to be the picture from this. Here you really see the drifting peaks. So I don't understand this drifts qualitatively. This is the honest answer. Okay. So let me ask a question. Can you do astroseismology of neutron stars using all of this? So perhaps the intermittent QPOs, they probe shear modes of the crust. So that's pretty cool. But for me, more exciting is that indeed the slow frequency, the lowest frequencies around 20 hertz, they probe Alfven speed in the core. So I think that can be quite remarkable to get a sense of what Alfven waves are doing in the core just from seismology of a neutron star. Now, to get this 20 hertz, to get the right number, right, to get these frequencies, what I actually need to do, I need to decouple 95% of the core material from the wave, right, just to get the right numerics. And that's actually not so strange because if the neutrons are superfluid, they decouple. Right, they decouple from Alfven waves.
What about having a stronger field in the interior instead?
That's also a possible solution. So stronger field or different geometry where you have shorter loops. So that's why I'm not saying this is an evidence for neutron superfluidity. I'm just saying it's pretty cool, right? That this is one of the parameters which enter into your consideration. How much of the core is decoupled. But so let me just talk about the caveats of this whole business. One caveat is that I really haven't addressed what produces QPOs and X-rays, right? I've just talked about dynamics of neutron star as a whole. But how dynamics of neutron star as a whole produces strong modulation in X-rays, that's an unsolved problem, and people haven't solved it. So this is an important problem to address. And until we are confident that this is really, we understand how the motion of a neutron star surface is reflected in modulation of the X-ray luminosity, we can't really say with confidence that we are seeing a motion of a neutron star surface. The second point is Yanchin's point is that indeed the strength and geometry of magnetic field can be different. Geometry is almost certainly unrealistic, so one of the things is to do it from realistic geometries, for example, like Jonathan is finding in stars. And so Martin van Hoven in Leiden is doing a thesis with me on this problem, sort of doing this problem, but for more realistic field geometries. It turns out to be really non-trivial. And the third point is that are neutrons really decoupled? Because I said, okay, neutrons are superfluid, they're probably decoupled. But in fact, if you ever listen to people who work on interiors of neutron star talk about this, they'll tell you that neutrons are not decoupled at all, that neutron vortices are strongly magnetized, all right? This is a neutron vortex. But because nuclear forces, they have some velocity dependence, then the neutron supercurrent which goes around this vortex, it carries some charge, it carries some protons with it. And so this vortex becomes strongly magnetized. Okay? And then if protons are a type 2 superconductor, right, then the magnetic field is in flux tubes, and then these vortices can interact with flux tubes quite strongly. Right? So it's not obvious, actually, in this picture that neutrons are dynamically decoupled from Alfven waves. So what we have done recently with Martin van Hoven is to consider how do Alfven waves propagate if on top of if the neutron superfluid vortices are strongly pinned to this magnetic field lines. Okay, and then you have a magnetic field which feels magnetic restoring force, but it also feels the Magnus force from the motion of these vortices through a superfluid. So the picture is that you have a vibrating charged component, all right, and then these flux tubes go together with the charged components, but the vortices get stuck to the flux component, and then they move along with the flux component, and when the vortex moves through the superfluid, it feels the sideways force from a superfluid, which is called the Magnus force, which is analogous. If you kick a soccer ball and it's spinning, then the soccer ball will feel a sideways force due to a combination of its motion in the air and the spin. So this will produce a sideways force. There is a similar thing that a superfluid vortex feels as it moves through a superfluid. It feels a sideways Magnus force. And this does modify dispersion relation for Alfven waves, so you can calculate what it does to Alfven waves. Now, fortunately, it turns out that magnetars are really slowly spinning. So the frequency shift due to this Magnus force, it goes like this. It's a spin angular velocity of the star divided by the frequency of the wave, and multiplied by this ratio of neutrons to protons, mass ratio. Now, this is about 20 for neutron stars. But what saves you is that the magnetars are so slowly spinning. You know, they have spin periods of 5 to 10 seconds. So they basically don't have so many vortices in their interior. And so this number comes to about 10%. So, which means that if neutrons are superfluid, then they are decoupled from magnetar Alfven waves. So at least there is no uncertainty in how many neutrons are coupled to these Alfven waves. But there is still uncertainty in geometry in the strength of magnetic fields in this object.
Does decouple just mean that when you calculate Alfven speed b squared over rho, it just takes the rho of the photons only?
Yes, you take the rho. That's what it means. Right. Okay, so my conclusions for magnetars is that the steady QPOs, my bet is that they're not some kind of crustal frequencies, but that they're special points of the Alfven continuum of the core. And by observing the steady QPOs, you can probe the structure of magnetic field inside the neutron star. That you see intermittent QPOs everywhere, at least in the model, but they get enhanced near crustal frequencies. So perhaps by looking at the intermittent QPOs, you can infer something about natural frequencies, torsional frequencies of the crust. There is some qualitative agreement between theory and observations, and okay, you can probe Alfven speed in the core, and there is a big open issue, which is magnetosphere. Now, how am I going for time, Pat?
You're about
Out. Okay, if you want to ask me about measuring gravitational waves using pulsar timing array, you can do it after the talk.
So in the initial part, when you measured the modes using the
Yeah.
But these two are supposed to represent the same physical model, right?
Yes.
A coupled Alfvenic system. In the second picture, first of all, that's an explicitly positive definite system of this couple harmonic oscillators
Yeah.
with real eigenvalues. Your interpretation would be that there is some either a lowest mode or a bunch of lowest modes at around 18 hertz. Wouldn't that
I suppose so. You have been saying it, and I'm kind of agreeing with you, but I'm not sure. I haven't done this calculation.
10,002 are guaranteed to have 10,002 eigenvalues. I can diagonalize that system. It's guaranteed to have them, and you'll never see oscillations at the lower eigenvalue than the real one. So the fact that you see it improves that this system must have a low eigenvalue.
I suspect that you're right.
Which means your previous system must also have an eigenvalue because it's the same equation you're solving at 18 hertz, isn't it?
No, the previous system doesn't have an eigenvalue. If you go to the continuum limit, you'll find that you have no eigenvalues.
But it's the same equation you're solving.
Well, let me prove to you an anti-eigenvalue theorem, all right? Let's suppose that you take this... sorry, it's not answering your question directly. It's just, discussion, right? Let's suppose you take this oscillators, right? Oh, where was it? Here. You take this... let's suppose you make this oscillators into a continuum, okay? And suppose I go by the opposite. Suppose the mode exists. Meaning, suppose there is a mode such that the crust is moving with some fixed real valued frequency. Okay, that's what you're advocating. Now, if this real valued frequency is somewhere in the range between the 2 points of the continuum, you get into contradiction because it will pump this oscillator on resonance, and it will pump it to infinity. It will increase the oscillators which are exactly on resonance. They'll increase the amplitude infinitely, right? If you take a pendulum and you move on resonance, the foot point of the pendulum, it will linearly increase its amplitude until it saturates by some linear mechanism. So that's not a normal mode. So let me put it this way: you can't have a normal mode if you have a continuum. You can't have a normal mode where the big pendulum moves, and it has a frequency which is somewhere in the range of this continuum.
That's not to say that proving that your whole linear infinite dimensional system does not have the lowest eigenvalue. Those are statements that you did one. You're saying as you add more and more strings to it.
So my guess.
And diagonalize this. If you just ask what does the lowest eigenvalue do, it either becomes multiplicatively degenerate, or it converges to a finite, or it runs off to infinity, or it converges to a finite boundary.
So
those are only three options. Well, you can then become infinitely degenerate, for example, in which case, as what you were saying, it blows up in some
yeah.
sense. But it's still there. It just gets very strong, which is what you're seeing.
Right.
What about energetics? We see this transition amplitude in the signal, observed signal.
Yeah.
And if you decompose it, because you said you first have it and then
Yeah.
follow decay. What kind of crust amplitude you use initially?
Now, I actually don't. I think it's a power law decay in the simple toy models like this. I'm not sure it's still a power law if you have something more complicated, like many crustal modes and many Alfven oscillators which have.
Can you do a one-to-one method, like a twist is by all unity, and you get such an amplitude?
Yeah. Well, you're saying. Your basic question is whether you can get the QPOs of observed magnitude, right? Because you have decayed substantially. I think that's absolutely crucial question. Since we don't have model how these QPOs are produced from oscillations. Yeah. How do you? Okay. I've talked about how neutron star oscillates, but I haven't talked about how this translates into X-ray luminosity. So before I know how oscillations of the stars translate into X-ray luminosity, I can't tell you anything about energetics. But I suspect this is a very important question, of course, because exactly this, if your initial energy is stored in the crust, you really drain substantial amount of this energy into the core. Okay, it's actually quite cute to think about how. Let me just say one more thing. There is some other cute part of the system here about this system. Let me now, instead of damping each of those oscillators individually, let me put damping between them. Okay, so frictional damping between them, which corresponds essentially to some viscosity between these oscillating cylinders. And let's watch the energy of the system. So you deflect the system, you let it go, and you see what is the rate of power that the system damps. Okay, it turns out to be very interesting because initially these oscillators are pretty much in phase with each other. So there's very little shear between them. So for a long time you'll have very, very little power dissipated. But then they get linearly out of phase with each other, and the shear increases linearly with time. And so then the power which is dissipated, it shoots up because it increases quadratically with time. So it's very unusual, right? You start with this large amplitude. You see immediately the dissipation of the pendulum. So you think, oh, it must have all dissipated into heat. But it hasn't. It's still sitting in the small oscillators. And it's when the small oscillators become sufficiently dephased, then all of a sudden it shoots up. Shoots up there.
So if you go to the continuum limit, then you won't have ever.
Oh, you will. In continuum limit, you have shear viscosity, right? So in fact, in the continuum limit, it doesn't depend on. So, but your basic point is that if you start with a deformation of the crust, you dump a lot of energy in the core, and it's not clear that the amplitude of motion of the crust later on remains big enough to power substantial QPOs. So I agree with this. This certainly has to be investigated.